and welcome to our series for maths teachers in the FET phase and of course everyone else who's interested in education in South Africa. In this module we take a further look at trigonometric functions, but first up let's look at our video. When one looks at what appears to be the path of the International Space Station from Earth, one is stunned by how nature is related to trigonometry. The path takes the shape of a sine graph with the equator as the x-axis. Sound is also said to travel on a curve like the sine graph. At Komhaha High School in KwaZulu-Natal, the teacher, Mr. Naidu, is beginning a lesson to determine the effects of constants on trigonometric functions.
Okay, on your table right now, I've placed the picture of a sine graph. And I want you to make a note some of the properties of the sine graph that you're looking at. Remember that we are looking at the sine graph from a negative 360 degrees to a positive 360 degrees.
The outcomes of the lesson for the learners are to predict how multiplying the angle by a constant affects the sine graph, to determine the effect on the graph of multiplying sine of the angle by a constant, and to draw the graphs and compare their features with the normal sine function graph. The lesson begins with a recap of the properties of the sine graph.
If they have a good understanding of the parent function, then we will use various techniques of group work, discussions, them drawing, using the calculator work, to arrive at a conclusion as to what would happen to the parent function if the sine function is multiplied by some constant. And then we repeat the same process for what would happen to the sine function if the angle, the theta value, is multiplied by some constant. Okay, where does this function cut the x-axis? Yes?
Negative 180.
Negative 180.
And positive 180.
Positive 180.
And 0.
And 0. But if we look very carefully, you'll find that this sine function also intersects the x-axis at two other points.
Negative 360 to positive 360.
I was looking for things like the intercepts. Do they understand where the graph cuts the x-axis? Do they also understand the concept of the range of the graph? That means all the possible y values of the graph. Do they understand the domain? That means all possible x values. Do they also understand where the graph is turning? If the amplitude is 1, then what is the range of this function?
Negative 1.1.
Excellent. Can you give me the maximum turning point?
90 and 1.
Minus 270 and 1.
Minimum turning points on that function.
270 degrees and minus 1.
If the kids are able to understand that just from looking at the parent graph, and also algebraically look at the relationship of some of the properties of the sine function, I think then working with them through the process of what would happen to the sine function if it is multiplied by a constant would become that much easier. They would see what would happen to the turning point of the graph, for example, at 90 degrees and 1. What happens to that value if it is multiplied by 2?
Now that the learners are familiar with the graphic representation of the sine function y equals sine theta, the teacher will introduce the new concept that is multiplying the function by a constant. Let us call this constant A.
The graph that we are all looking at is a graph of y is equal to 1 sine 1 theta. What happens now if I multiply this sine function by 2?
In other words, y equals 2 sine theta. After working out the calculations, the learners complete the new graph.
What has happened to the turning point that you had 90 degrees and 1?
The turning points will be increased.
Okay, what will the point now be? 90 degrees and? 90 degrees and 2. Did all the turning points change? All the turning points change. How far? What is the range of those turning points?
The range is negative 2 and positive 2.
After establishing a pattern by getting learners to multiply the function by different constants, the teacher will ask the learners to predict.
If the child is able to follow through a series of instructions and arrive at a prediction by himself or herself, I think it's far more valuable than me as a teacher saying, this is what's going to happen at the end. I think that the child will learn far more in that way because they were part of the discovery process. If I change the A value to 5, do you think you'd be able to predict what would happen to the turning points?
The range would be 5 to -5.
Let's say that again. Should be from -5
Yes,
to positive 5. Remember, on the number line, we read our values from the negative to the positive. Okay, what happens if I change the A value to half? So what would be the range?
-half to half.
-half to positive half. Excellent.
Learners draw the graphs with the new values.
If I relied purely on prediction, without the children doing some practical drawing of the graph, I think it would not have solidified that conclusion at the end. I think by using a graph that they could see, they could work on physically, and follow the instructions given to them, they were able to come to the necessary prediction that we wanted. So we have changed the A value of the graph. We all can predict what is going to happen to the sine function when I multiply it by a constant.
The teacher summarizes by stating that y will have a positive maximum and negative minimum value related to the value of the constant. In the next activity, the teacher discusses the effect of multiplying the angle by a constant. Let us call this constant b. That is y equals sine b multiplied by theta.
What will happen now if I have to change the b value? In other words, I multiply the angle by a constant. The value in front of the angle has now been changed. Previously, it's 1 theta. Now I've changed it to 2. Draw a sketch for me that would represent this function.
Whilst the learners are drawing the graph, the teacher moves between the different groups and encourages discussion.
You've got two curves from 0 to 360. When do I see the first complete one? From 0 to 180. And you see it repeating itself from? Okay, so how many graphs have I got altogether now? From 0 to 360? 2. To the board.
When the teacher has heard the learners' viewpoints, he reports back to the whole class and begins with reference to the original graph.
This sine function is y is equal to 1 sine 1 theta. I have now changed it to read y is equal to sine 2 theta. I have multiplied the angle by 2. What is the period of the normal sine function? This one here. What is the period of the normal sine function? How many degrees? Okay, 360 degrees. But now, when do you see a complete sine function?
It's 180 degrees.
From 0 to 360 degrees, how many sine functions do you see?
2 sine functions.
You see 2 sine functions. Okay. What is the value of b? Value of b is 2. And she says the value of b is 2, and I now see 2 sine functions in 360 degrees. What is the period? When do I see one complete sine function?
180.
We have one sine function in 180 degrees. Let's go back. Is there a relationship between the 360 and the 180?
You said 360 degrees divided by 2, then you get 180 degrees.
Very good.
Now that the learners have established the effect of multiplying the angle by a constant, the teacher can ask learners to predict an outcome.
Okay, what if I change the b value to 3? Write on the function for me. Y is equal to sine 3 theta. Write it down. The period of the graph is now?
120.
He says the period is 120 degrees. How did he arrive at that answer, 120 degrees?
We divide 360 by 3.
We divided 360 degrees by 3. How many sine functions will I see from 0 to 360 now?
3 curves.
I will see 3 functions from 0 to 360 degrees.
One of the problems that learners should overcome is the use of incorrect terminology when relating to periodicity of the graph.
So when I ask the question, how many times does it repeat itself, they have an understanding of the word repeat, rather than saying what is the frequency of the graph, what is the periodicity of the graph. But at the end of the lesson, I must admit that we need to bring in that mathematical concept of period, because they need to understand that when I that the two concepts are synonymous. How often does it repeat itself? What's the frequency, or even what is the period? They're all synonymous terms. The B value is now half. Can we predict? Can we predict? Yes.
The period to be 720.
The period is 720. That is strange because I draw my graph from 0 to 360. So how did we get 720?
We divide 360 by half.
We divided 360 by half. So 720 degrees is now what? The period. So I will see one complete sine graph. I will see one complete sine graph where? It's 720 degrees. But my domain is 360. So how much of the picture do I see in 360 degrees?
Half of the curves.
Excellent. In 360 degrees, I only see how much of the picture? Only half the picture. So the B value indicates to me exactly how much of the picture I will see, how much of the function I will see in 360 degrees. It also helps me to find the period of the graph. By taking 360 degrees and dividing by half, I will get a period of 720 degrees. We now can predict what happens if I...
In this lesson, the teacher has accomplished his outcomes. Learners now know how multiplying the function sine theta by a constant affects the graph, as well as how multiplying the angle by a constant affects the sine graph.
The learner needs to understand the fact that the trig graph is repetitive, the fact that your intersections are mirror images of each other, and when they can see that connection, they will then be able to understand that it is simple. I just have one concept, and what I'm going to do to it now is I'm going to change the features of it, but the actual concept remains the same.
Now that we've seen our video, it's time for us to welcome our guests for today's session. We've got Peter Middleton from Protech, we've got Modiehi Ligwane from the Gauteng Department of Education, and we've got Taska Matlejwane from Pafokgang Secondary School. Thank you very much for joining us. The first question, let me start with you, Taska. What is the value for learners of manipulating the sine function as we saw in this lesson?
Yeah, I found the lesson being very important in the sense that it is important for them to see what the constants does to a function. We've got only one function, y equals to sine theta. And now the constants that which are attached there, like a as a coefficient of sine theta, it affects the function differently as from that of b. Now it was good that they went through different amounts of a to show the learners how the range is being affected. That I think I would agree with them. It was well done.
Okay. Modiehi?
The constants, as they are introduced, really they indicate how they affect the amplitude, as he has mentioned. And the learners should not just cram and say, okay, a sine function is like this. It runs from maybe 0 to 1 or 0 to 2 only. It can go up depending on the constants that are introduced in the function.
Peter, can you add to that?
Yeah, well, for me the amplitude is a key issue because of real life and how sine and waves manifest themselves in real life. Because what you're seeing here in terms of 1 sine 1 theta is a mathematical expression which is a massive oversimplification of life. And therefore I think it is vital to get that translation, that how things change and how things are not so complicated and how you can simplify it just by understanding what happens when you multiply something.
Okay. Modiehi, why do you think it's important for learners to draw the graphs themselves as opposed to watching the teacher doing it?
As we mostly know, really there's no learner that can master mathematics or even get to know a bit about mathematics if they don't practice. With mathematics you have to practice every day, and if the educator is going to do it for them, then they're not going to get into the drive of really on their own doing it, because they need to practice even for the exam. You have to be quick in the exam to see, oh, it's a sine function or it's a cos function, then it should go this way. You know, automatically you already know through practice. And also, you also are able to relate it to other subjects. For instance, the skill of drawing a graph. In other subjects also, you need to know the point, where the point is. The educator indicating that a sharp pencil is very important to indicate the point. A pencil that is not sharpened will not give you the right point. Joining those points together, you may miss you may miss the graph, how the line goes to join those points together. It's very important, it's very integral.
Actually, I would agree with them that doing these things on their own, when learners lay hands on the sketching of the functions and so on, is part and parcel of constructing knowledge. And that knowledge will only make sense to learners as they construct it themselves. Learners don't learn by what the teacher is telling them. They've got to internalize what the teacher is saying and reconstruct their own ideas about what the teacher is saying. And that will be emphasized by, as they are sketching the graphs themselves, they start to learn something.
Okay, Peter?
Yeah, no, I tend to agree entirely. I don't think I have too much to add on that one. I think for me it's fundamental. You learn by doing. You don't learn by watching somebody else.
You have to do it yourself.
Yeah.
Now, what is the value of discovery learning, as we saw in the lesson?
Well, to build onto that, I think that's the key issue. You learn, if you like, by doing something and by exploring it and by turning it on its head for yourself. Nobody can tell you how something works, and if they do tell you, you will always internalize it differently from what they are saying it. Doesn't necessarily mean that you've got it wrong. It just means that you have taken ownership of that knowledge and you have made sense of it. Now for me, those are the words I like, and in terms of mathematics. Understanding is the common word. For me, it's much more important that kids make sense of something. And you can only make sense of it if you have gone through that discovering process yourself. And a teacher may think, oh, this has been discovered by Newton thousands of years ago. But the point is, you have to rediscover it yourself. You have to go through it. You have to have had something light up in your brain, some excitement, some realization, oh, this is easy, to take and internalize and make sense of what you are seeing.
Okay. Jay, add to that?
I think it's very important to discover on your own, because it brings out the excitement in whatever you are doing. You also get to change your attitude in what you really are doing, and that is very important for mathematics learners.
Okay, Taska?
Yeah, I couldn't say it in any better ways except to say this discovery method is a fair way of giving learners a chance to discover our new scientists. We still have a lot more Einsteins and Newtons, and if you don't give them the opportunity to discover these things, you kill maths and science.
Sure. Mujay, could more group work have benefited the learners, do you think?
I should think so. They were divided into groups, but I think those groups were too big. In a big group like that, you find that some learners depend on the others on answering the questions. They really don't get involved. Even if the educator, it was indicated that he was moving around to check what the groups were doing.
So you have learners that essentially don't know much about it and are not learning from the experience, where they have other learners who they can just sit back and know that they will do the work for them.
Exactly.
It goes a long way when it comes to group work. Peter?
Yeah, I think the size of I like the size of the graphs, because you had nice big graphs that they were all working on. I kind of like that. It is a difficult one. To have a group of kids working on one graph is actually quite difficult. You can only one person can draw it at a time. But I think they did the size quite well. I'm not sure that I wouldn't have additionally to that, and I'm sure he probably would have got the learners to actually do it for themselves as well as that. It's nice to have them discuss something big and then actually get down and do it. Each one do it. So I think, it would have been nice to have more group work, but the opposite is also true. Learners also need to engage this as individuals.
Okay, Taska?
Yeah, group work is always important. I would say more group work is important, because self-discovery comes from there. There are challenges which flow from the peer group pressure as well, and also the relaxation that every one of them wishes to contribute. I think group work, it's a fantastic way of teaching. It's a good tool. I would go for group work, as CAA has done.
They also get to remember more of what was said by a peer group, and also they learn from each other.
They pick it up better, probably.
They pick it up better
than they would from a teacher, I suppose.
Mm.
Okay. Any other issues you'd like to raise, Tasa?
Yeah, I'm a bit worried about the misconceptions that which comes through the language used by the facilitator or the educator. Mm-hmm. I think the mathematical discourse needs to be looked into very carefully there. Mm-hmm. Like, for instance, I was worried when he was asking, for instance, at some stage, say, how many sine graphs, you know, as if maybe it will help him to introduce a question of the periodicity. How many periods do you have there, or the interval? Now, I realized that the language, the way it was used, it could end up confusing learners, not knowing the difference between the interval versus the period.
Mm. Okay.
I could say at some stage there was an answer of 720 whereby the educator was saying 360 divided by a half. You know, I think even though it looks so simple, it's important for the educator to really bring up again the issue of dividing by fractions. You know, like most learners have a problem there also, that dividing by a fraction is the same as multiplying by its reciprocal. How did you come up with 720, such a big number? He didn't really break it down to indicate how he got that. And from a maths class, it is very important, because when you go to other classes like your biology and science, we use the same principle, and then they want to know you still have to teach mathematics before you teach science, which becomes difficult.
So integration there would be an important part of this.
Yes.
Peter?
Yeah, what I'd like to have seen would be some reality. And there's lots of opportunities for this. For example, our 220 volt supply that comes out of our electricity sockets is an exact application of A times sine theta. It's 220 times sine theta. That is what our alternating current is doing. And the amplitude of a real wave, that amplitude is that constant. The repetition is coming out of. And I would have liked to have seen some of that brought in, because that whole reality thing, this is relevant, this is part of life, needs to come out of mathematics as often as we can.
Okay. Well, that's all we have time for this session. Thank you very much to our guests for your input. Very valuable. And thank you to our viewers at schools and at home for watching. Do stay tuned for Module 16 coming up soon. Goodbye.